In this video, we shall try to understand how to use scientific notation to convey the number of significant figures without any confusion and without needing any convention. In the last video, we understood that integers with trailing zeros are a problem. If you are given these three measurements, it is impossible to tell whether the trailing zeros are part of the original measurement or if they are inserted during a unit conversion. And to overcome this confusion, we came up with two different conventions. And these conventions are annoying. So is there a way to convey the number of significant figures without any confusion and without depending on such conventions? I think there is a way. Remember, we ran into this confusion only in case of integers with trailing zeros. We did not have any problem with decimals, whether there are trailing zeros or not. We were able to figure out the significant figures without any confusion for any decimal. So, to avoid these conventions, what if we can write this integer as a decimal? We had no problems with decimals, right? So all we have to do to avoid this confusion and the need for such conventions is to write this integer as a decimal. So all I have to do is put a decimal point somewhere in this number. Now the question is, where should we place the decimal point? Remember, earlier we established the fact that the location of the decimal point in the number has no effect on the precision or the number of significant figures of the measurement. So to convey the precision or the number of significant figures of a measurement without any confusion, we have the freedom to place the decimal point anywhere we want. Because we have the freedom to place the decimal point anywhere we want, I choose to put it between this 1 and 6. Now you would understand shortly why I chose this particular location for the decimal point. Now mathematically, there is an assumed decimal point at the end of the last digit in every integer. So this is what we have initially. I am not talking about these conventions. I am saying mathematically. But I wanted this decimal point between these two digits. So we have to move the decimal point by 4 places to the left of its current place. And for that, you have to divide it with 10,000. Now, when you divide a number with 10,000, you have changed its magnitude. So, to keep its magnitude same, you also have to multiply it with the same number. Now, because of this division, this decimal point moves by 4 places to the left of its current position. Then it becomes 1.6100 multiplied by 10,000. Now we can write this number as an exponent for convenience. We can write this as 10 to the power of 4. So what we finally have is 1.6100 multiplied by 10 to the power of 4 milligrams. And this is what we call scientific notation. So we represented our measurement in scientific notation. Okay, we wrote this integer as a decimal multiplied with something. Now the question is, did we convey the number of significant figures correctly? Now by looking at this decimal, can you tell the number of significant figures? You know how to do that. There are 5 significant figures in this decimal and the original measurement says the same. So we are able to convey the number of significant figures correctly by writing this integer as a product of a decimal and an exponent. Now how do we convey that there are 4 significant digits in this case? We can write it as 1.610 multiplied with 10 to the power of 4. Now when you multiply this with 10 to the power of 4, you will get back your number. But if you look at this decimal, it has 4 significant digits and that's what we wanted to convey. So job done. Now in this case, how do we convey that there are only 3 significant figures? Simple. Write it as 1.61 multiplied with 10 to the power of 4. Now when you multiply this with 10 to the power of 4, you will get back this number. You know how to do that math. And if you look at this decimal, you would understand that there are only 3 significant figures. And in this case, we wrote it as 1.6100 multiplied by 10 to the power of 4. So in all these 3 cases, we represented the number of significant figures correctly without needing any convention, just by writing them as products of a decimal and an exponent. And this is what we call scientific notation. So what we did here is we represented these measurements in scientific notation. And here is the general form of scientific notation. It is a product of 2 terms. This term is called the digit term or the significand, and this term is called the exponent term, and this E is called the exponent. And remember, the magnitude of the significand must satisfy this condition. It is very important. This means there can be only one non-zero digit to the left of the decimal place in the significand. That is what this means. In the scientific notation, this exponent term tells the location of the decimal point in the original decimal. That is the purpose of this exponent term. Because the location of the decimal point does not affect the precision or the number of significant figures, you can totally ignore this exponent term to determine the number of significant figures. All you need to determine the number of significant figures is this significand. Now with that, we can start working out some examples. Now let us work out some examples. Let us write some measurements in scientific notation to convey the number of significant figures without any confusion and without needing any convention. In the first measurement, we have the number 1, and you know it has one significant figure. And how do we convey the same by using scientific notation? I think we can write it as 1 multiplied by 10 to the power of 0. You know 10 to the power of 0 is 1. When you multiply 1 with 1, you will get back your original measurement. And this is the exponent term and this is the significand. And to figure out the number of significant figures, all you need is this significand. We can totally ignore this exponent term. And by looking at this, we can understand that there is only one significant figure. By the way, how many digits are there in the significand? Only one digit, right? So let us write it here. In the second measurement, we have the number 30. Again, we have an integer with a trailing 0 but without a decimal point at the end. So by convention, that means this 0 is not significant. So in this, there is only one significant figure. But how do we convey the same by using scientific notation? I think we can write it as 3 multiplied with 10 to the power of 1. 10 to the power of 1 is 10. When 10 is multiplied with 3, you will get back your 30. And to know the number of significant figures, all we need is this significand. And by looking at this significand, we can understand that there is only one significant figure. And how many digits are there in the significand? Only one. And in the next example, there are 3 significant figures. And how do we convey the same using scientific notation? I think we can write it as 6.89 multiplied by 10 to the power of 2. And to figure out the number of significant figures, all we need is this. And by looking at this significand, we can easily understand that there are 3 significant figures. And how many digits are there in the significand? 3. And in the next example, we have again an integer. And in this integer, this leading 0 does not contribute to the magnitude of this number, so it can be ignored. So there are 5 significant figures in this measurement. Now, how do we represent that using scientific notation? I think we can write it as 3.9871 multiplied by 10 to the power of 4. And to know the number of significant figures, all we need is this significand, and from this you can easily figure out that there are 5 significant figures. By the way, how many digits are there in this significand? 5. And in the fifth example, again we have an integer with trailing zeros but without a decimal point at the end. So that means by convention, these 2 trailing zeros are not significant. So there is only one significant digit in this measurement. How do we convey the same using scientific notation? I think we can write it as 2 multiplied by 10 to the power of 2. 10 to the power of 2 is 100. When you multiply that with 2, you will get back your 200. And by looking at this significand, we can easily understand that there is only one significant figure. And by the way, how many digits are there in the significand? Only one. And the next measurement we have is the number 130 with a bar on this number 3. By convention, that means this 3 is the last significant digit in this measurement. So this 0 is not significant. So there are only 2 significant figures in this measurement. And the same can be represented by using scientific notation as 1.3 multiplied with 10 to the power of 2. 10 to the power of 2 is 100. When multiplied with 1.3, we will get back our 130. And by looking at this significand, we can easily understand that there are 2 significant figures. And the number of digits in the significand is 2. And in the next measurement, we have a negative number. And for the purpose of figuring out significant figures, you can ignore its sign. It doesn't matter. And there are how many? 6 significant figures in this measurement. And the same can be represented by using scientific notation as minus 8.01908 times 10 to the power of 1. And by looking at this significand, we can easily understand that there are 6 significant figures. Also, there are 6 digits in this significand. And in the next measurement, because there is no decimal point at the end, this trailing 0 is not significant. So there are only 4 significant figures in this measurement, and it can be represented as 1.866 times 10 to the power of 4 in scientific notation. 10 to the power of 4 is 10,000. That is, you have to move the decimal point by 4 places to the right. So you will get back this number. So this is right. And by looking at this significand, we can easily understand that there are 4 significant figures. And the number of digits in the significand is also 4. And here we have 1.00. And you know there are 3 significant figures in this measurement. And it can be represented as 1.00 multiplied by 10 to the power of 0 in scientific notation. And by looking at the significand, we can understand that there are 3 significant figures. And the number of digits in the significand is also 3. Again, how many significant figures are there here? 1, 2, 3. And it can be written as minus 3.45 times 10 to the power of 1, 2, 3 minus 3. Now when you multiply this with 10 to the power of minus 3, you have to move the decimal point by 3 places to the left. So that will give you back this number. And by looking at the significand, we know that there are 3 significant figures, and the number of digits in the significand is also 3. In the next measurement, we have only 1 significant figure, and that can be represented as 3 multiplied with 10 to the power of minus 1 in scientific notation. And this significand tells clearly that there is only 1 significant figure. Also, there is only 1 digit in the significand. And in this measurement, there are 6 significant figures, and it can be written in scientific notation as 1.90983 multiplied with 10 to the power of 5. And by looking at this significand, we can easily understand that there are 6 significant figures. Also, there are 6 digits in this significand. And in this measurement, all these trailing zeros are not significant because there is no decimal point at the end. So there is only 1 significant figure in this measurement, and it can be represented in scientific notation as 6 multiplied with, how many zeros do we have here? 3, 6, 9, 12, 15, 18. So 6 multiplied with 10 to the power of 18. And this significand clearly tells that there is only 1 significant figure. Also, it has only 1 digit in it. And here we have how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 significant figures. It can be written in scientific notation as 7.500000001. How many zeros did I write here? 3 plus 3, 6 plus 1, 7. How many do we have here? 3 plus 3 plus 1. Yeah. So multiplied with 10 to the power of 9. And by looking at this significand, we can understand that there are 10 significant figures without any confusion. And also there are 10 digits in the significand. And in this measurement, there are 4 plus 3, 7 significant figures. And it can be written in scientific notation as 1.409200 multiplied with 10 to the power of 2. And this significand clearly tells that there are 7 significant figures, and also it has 7 digits in it. This measurement looks as if it is already in scientific notation, but it is not. See, the magnitude of this term is less than 1, but for it to be in scientific notation, the magnitude has to be between 1 and 10. So this is not in scientific notation. But how many significant figures are there in this measurement? There is only one significant figure, and the correct way of writing it in scientific notation is 7 multiplied with 10 to the power of 1. The magnitude of this significand must be between 1 and 10. And this significand tells that there is only one significant figure and there is only one digit in it. Again, the same problem here. The magnitude of this term is more than 10. So this is not in the scientific notation. But how many significant figures are there here? I think there is only one significant figure here. Because there is no decimal point, these trailing zeros are not significant. And the same can be written in scientific notation correctly as 2 multiplied with 10 to the power of minus 2, I think. And this significand clearly tells that there is only one significant figure and it has only one digit in it. Now here you may have noticed one pattern. The number of significant figures and the number of digits in the significand are the same in every case. And this is possible because of this condition. See, in all these examples, the magnitude of the significand is between 1 and 10. Only when its magnitude is between 1 and 10 is this possible. That is, the number of significant figures will simply be equal to the number of digits in it or in the significand. So, if it is in scientific notation, to know the number of significant figures, all you have to do is count all the digits in the significand, as simple as that. And it is for this reason we chose this particular place for the decimal point. So scientific notation can be used to convey the number of significant figures without any confusion for any measurement, whether it is an integer or a decimal. In addition to that, scientific notation can be used as a shorthand notation to represent some really large numbers. This is the experimentally measured value for Avogadro's number. And can you figure out the number of significant figures in this value? Because there is no decimal point at the end, all these trailing zeros are not significant. And the rest of the digits are all significant. So we have how many? 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 significant figures. Now, how can we represent this in scientific notation? We can write it as 6.02214076 multiplied by 10 to the power of 23. And this is the radius of the nucleus of hydrogen atom, approximately. And this can be written as 7.5 multiplied with 10 to the power of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, minus 16 meters. So, scientific notation can be used as a shorthand notation to represent some really large or some really small numbers. And it can be used to convey the number of significant figures without any confusion as well.